Welcome to Structural Analysis 2 video series. Unit number 3, Flexibility Method. Lecture outline, numerical problem on continuous beam. So this problem is divided into three parts. This one is the first part of a problem. Problem statement is as follows. Analyze the two-span continuous beam shown in figure by flexibility method. Draw bending moment and shear force diagram. Now in the given figure, AB span is loaded with the 20 kN per meter UDL, moment of inertia 2I, and span AB is equal to 6 meter. Now span BC is equal to 4 meter in length, moment of inertia I, and loaded with 80 kN point load at mid span. CD is cantilever portion loaded with the 40 kN point load at free end D. CD is equal to 2 meter and moment of inertia is I. Now at A there is a fixed support and at A, B and C there are hinge supports. First step in the problem to calculate degree of static indeterminacy. So to find out degree of static indeterminacy, first we have to calculate number of reaction, those are unknown. So now neglect the horizontal reaction, okay, and also neglect the summation of fx as equilibrium equation. So neglect that equation, don't consider that equation, summation fx, and also don't consider horizontal reaction. So at A there is a fixed support, so unknown reactions are 2. At B there is a hinge support, so unknown reaction is 1, and also at C unknown reaction is 1. We neglecting the horizontal reaction. So total reaction is equal to 4, and equilibrium equation, those we have, those are 2. Again I repeat, neglect the summation of fx is equal to 0, only consider equilibrium equation 2, and one is a summation fy is equal to 0, and second one is a moment about any point is equal to 0. So therefore our unknown are 2 in number. So let's consider that degree of static indeterminacy is equal to 2. So and they are VB, vertical reaction at B, and second is vertical reaction at C. So these are the two unknown. Those are, let's consider acting upward and consider their sign as a positive. So first step is to find out the static degree of static indeterminacy and also their places. Okay. So Q is equal to Q1 and Q2. That means Q1 is equal to VB and Q2 is equal to VC. Now second step, find out dq, that is displacement corresponding to the redundant in the original structure. Now in an original structure, this VB and VC, these are the redundant. So whether there is any spring or displacement or sinking of a support at that particular location, no. So therefore the displacement is dq1 is equal to 0 at B, at redundant location B, no any displacement, so is equal to 0. At redundant location C, no any displacement due to the spring or sinking of a support, so is equal to 0. Okay, so these are the first two steps. Now next is, now draw the release structure with the load. Now release structure with load means the remove the redundant forces or the redundant forces at B and redundant forces at C. So remove that support B and C. So that is release structure with the load, but load you have to show. And second is the release structure with the Q1 is equal to 1. So remove the loads, only show the Q1 is equal to 1. And third one is a release structure with the Q2 is equal to 1. So let call it as m1, and from this you have to find out m1, m2 and capital M moment. Okay, so let's find out. First is our release structure with a load. So let's call it as a M. Now divide this structure into a different zone. So let's say D to C is a first zone. D to C is a first zone. Now keep origin D. Now D is our origin. Let's say 0 or O. Moment of inertia is I for span DC. Now limit. So starting point is D, which is on origin O, and DC last point is a C. So C is 2 meter away from the origin. So 0 to 2. Now take a. Now again then M means what? Moment of that. Uh, that means you have to take a section in on a CD and take moment about that section. So before that, let's see the sign convention. So right hand side of your section, if your moment is and clockwise, then your sign convention is negative because there is a hogging. If your moment is anti-clockwise, your sign convention is positive because of the sagging. So let take a moment of 40 kilonewton up to this section. Let's consider this distance is a x. So this 40 kilonewton will be rotate about this section xx in a clockwise sense. Therefore minus 40 into x. Now let for zone CD second diagram, let's say M1 diagram, let's call it as M1, that is Q1 is equal to 1. So that is M1 diagram. Now find out M1. So there is no any load in a CD, therefore that become 0. So this value is 0. The next one, next CD portion for Q2 is equal to 1. That means M2 diagram is release structure with Q2 is equal to. Now there is no any load toward the right hand side. So it become 0. Moment become 0. Now next zone is zone CE. So zone CE. Now C, location of C with respect to D origin. Let keep origin D as a constant. So location of C with respect to D origin is 2. So first limit is 2, and location of E with respect to origin D is 2 plus 2 4. So 2 dash 4 is a limit. Moment of inertia is I. Now take a moment about this x axis. So the distance is x. So 40 into x, it will rotate in clockwise sense. So minus 40 into x. Now next is release structure with Q1 is equal to 1 for M1. So no load, so it will be a 0. Next is your Q2 is equal to 1. Redundant Q2 is equal to 1. So now there is a redundant force toward the right hand side. The distance is x and it rotate in which sense? In a anti-clockwise sense. So it become positive. But now our origin is D. So it is that x we have to consider with respect to D. Our origin is D, not C. So this distance is x with respect to origin. We have to take with respect to origin. So this lever arm become x minus 2. So it is x minus 2 positive. Now force is 1. So it doesn't create any effect. Now next is EB. Next is EB. Span EB. Now let's take a consider section. Now how many forces toward the right hand side? There are 2 forces. Let's take first one is a 40. Okay, so before that let's put the limits. So for EB, E is again D is origin. So E is how much distance away from the origin? 4. So the first limit is 4, and B is how much distance away from the origin? 6 meter away from the origin. So 4 dash 6 is a limit. Moment of inertia is I, again origin is a T. So let's take moment of these two forces. So first is a 40, so the distance is x, so and it will rotate in a clockwise sense. So for clockwise the sign is minus, so minus 40 into x, minus 40 into x. Now next is 80 kilonewton. Now this distance with respect to origin is x, because this is our section. So lever arm is how much for 80 kilonewton? It is x minus 4. This lever arm is x minus 4 into 80, and it will be rotate in a which sense? It will rotate in clockwise sense. Therefore minus 80 into x minus 4. By simplifying, we have it minus 120x plus 320. Now next diagram, q1 is equal to 1. So our zone is EB. So take a section in EB. No force toward the right hand side, so it become 0. Now next is your Q2 is equal to 1. Again take a section in a zone BE. Now force appear toward the right hand side, only one force, and that is a Q2 is equal to 1. Again our origin is D. So this distance is x with respect to origin. So lever arm for Q2 is x minus 2. So x minus 2 into 1, and it will rotate about this section in a anti-clockwise, therefore positive. So positive x minus 2 into 1. Okay. Now next zone is BA zone. Next is BA zone. Now consider this x, consider this section in a BA zone. Now this is your origin. With respect to origin, this is, section is x distance away from the origin. Now how many forces toward the right of this section? 1, second 80 kilonewton, and third one is this UDL. So 3 moment you have to take. Okay, first one, let's take this 40. So this 40 will rotate about this section in a clockwise sense, so minus 40 into x. Second is 80. So this distance is how much? 4. So lever arm will be x minus 4. So minus 80 into x minus 4. Next is this UDL. Now find out this distance of a UDL. The distance. Find out this distance. So how much is distance? Total is x. X minus 6. So the distance is x minus, in term of x you find out x minus 6. So UDL is spread over the length of x minus 6 now. So convert UDL into point load now. The value of UDL is 20 into x minus 6 into x minus 6 divided by 2. This was in the lever arm. So take moment of this UDL about this section. It become clockwise sense, that's why minus. So minus 20 into x minus 6 into x minus 6 divided by 2. So by simplifying, we having minus 10 x square minus 40. Now next is your Q1 is equal to 1 for M1 diagram. Now take a section here in AB zone. Now D is origin. So distance of a section with respect to origin is x. Now how many loads toward the right hand side of this section? Only one. So find out lever arm for Q1 is equal to 1. So lever arm with respect to this x is this with respect to this section is x minus 2 plus 2 plus 2, that means 6. So x minus 6, and rotate in anti-clockwise sense, that means positive. So x minus 6 positive. Now next is last M2. So consider Q2 is equal to 1 diagram. Take a section in AB zone, and distance of this section with respect to D as a origin. Origin is D, and moment of inertia is 2I for that particular AB zone. And also about the limit. What about the limit? Now B. So how much B away from this origin D? B is away from the origin D is 2 plus 2 plus 2, that means 6 meter away. B is 6 meter away from D. So 6 is first. Now next coordinate is A. So how much distance A is how much distance away from D? So whole length is nothing but the location of A with respect to D. So that become 12. That's why 6 to 12 is a limit. Now we are interested in M2. So M2 is how much? Now this is X. So lever arm will be X minus 2. X minus 2, you will get lever arm for Q2. And it will rotate about the section in a anti-clockwise sense. So it become plus X minus 2. Okay. So this is a displacement analysis of a release structure. This is displacement. The remaining part we will cover in the next video. Okay. Thank you.